Good evening, ladies and gentlemen. Welcome to the latest lecture, evening lecture in the series that is making up this year's virtual Darwin Festival. Thank you so much for attending. It's great to see so many of you here this evening. Just a couple of things to draw your attention to. We will be having, I will be handing over, don't worry, I shall be handing over shortly. I should say my name is Tim Dawes. I'm your MC for this evening, and I'm a member of the Darwin Festival Organising Committee. I shall be handing over to our lecturer, Andy Newman, very shortly. In the meantime, can I just point out to you that on the bottom of your screen somewhere, you'll have a little button which says Q&A. If you've got any questions, please think about them during the lecture, or think about them now, and put them on the Q&A, and we will deal with them at the end of the session when we'll have a Q&A session. And we'll obviously deal with as many questions as we can. Hopefully, you'll all have something interesting to say from this. So the lecture will last about 30 to 40 minutes, and then we'll have as much Q&A as necessary, I suppose. I should also mention to you that this session is being recorded. Don't worry, it doesn't record anything that you do or say, but the lecture itself will be recorded, and like the other lectures, will then be available, made available on YouTube, which you can access via our website. And previous lectures are already available on that website. Okay, then let me just, it merely leaves me now to introduce Andy, who is Professor of Astronomy, Education and Engagement at Liverpool John Moores University, where he's worked since 1998. Previously, he did a PhD in astrophysics at Glasgow University. Andy's best thing, he says, about his job is it allows him to play with some very big telescopes all over the world and have fun with them. So let's hear what he's been doing with them. So without any more ado, I'm handing over now to Professor Andy Newsam. Thank you.
Thanks very much, Tim. And thank you all very much for coming along and spending your time here this evening. Hope it's worth it. So yes, I'm Andy. I'm an astronomer. So I'm going to be talking to you a bit today about some of the work that's been happening in this area in the northwest of and Midlands, basically within the UK, to try and understand more about things in the universe that change. I've called it things that go bang in the night because most of the changes I'm going to be talking about are pretty dramatic. But I'm going to be talking about this telescope that you see in front of us, why we built it, what it's been doing, and hopefully what we're hoping to do with it in the future as well. But I'm going to start in a slightly odd way. I'm going to tell you what astronomy is, which may seem a bit weird because you probably know what astronomy is, but actually it can mean quite different things to different people. For some people, it's about going out and looking at the night sky and knowing where the constellations are and being able to find your way around the night sky. And frankly, I'm rubbish at that. I can recognize 3 constellations on a good night. That's not what interests me in astronomy. What interests me in astronomy is that it's a branch of physics. It's about doing research. And so I'm interested in new physics. And if you want to learn new physics, if you want to learn new things about the fundamental nature of things, then you've got to push pretty hard. The easy stuff we've done, pushing little trolleys down slopes, wiring bulbs up to batteries, all that sort of thing we basically understand. What we don't understand is the more fundamental stuff, the really extreme things about physics. And there are ways you can try and understand those. You can build very large experiments. Many of you will have heard of the Large Hadron Collider at CERN, which is an absolutely enormous experiment. I mean, there are individual cameras, individual instruments on the LHC, larger than some cathedrals, absolutely huge. But there's another way of doing it, and that's looking out in the universe, because the universe is full of really extreme stuff. And obviously, it's as fundamental as it gets. It's got everything in it. And there are extreme things out there that we just can't make, we can't reproduce, even in giant experiments. The image in the background here is a good example. This is what's left of a star that we saw exploding a couple of thousand years ago. And it's called a supernova, and the outer parts of the star get blown off into space and produce this beautiful glowing cloud. But right in the center is something which you can't see. It's far too small to be seen in this, but we can detect it with things like radio telescopes. And it's what's left of the core of the star. And that core gets crushed down during the explosion, and it becomes incredibly dense. So dense that it squeezes together and it turns into something a bit like the nucleus of an atom. To give you an idea of how dense it is, we call it a neutron star, and a piece of neutron star about the same size as a typical mobile phone will weigh as much as Wales. And that's the country, not the animal. So it's insanely dense. Now, we can't reproduce things like that on the Earth. The Welsh won't let us. So if we want to understand things that dense, we have to look out into the universe. So to me, that's what astronomy, that's what astrophysics is all about. It's doing physics, learning new things about the universe, where you're treating the universe as a kind of laboratory. And that has lots of advantages. There are these extreme things out there that we can study, but it has disadvantages as well. And one of the disadvantages is everything in the universe is a really long way away. And that means it's very hard to spot it. I mean, this is what I might see if I went outside my house on a reasonably clear night in the middle of town. I'll see a few stars. Some of you might recognize the constellation of Orion there, and I'll see an orange glow. And that's pretty much all that most people see on a clear night when they go outside. If you can get out of town, get out into the wilds of Shropshire, then you'll begin to see something a little bit, you begin to see a little bit more. You begin to see a few more stars. You begin to see the glowing band of the Milky Way. And that's about as good as our eyes can do. If you've ever been lucky enough to go outside in a really dark place when the moon isn't up and it's nice and clear, and you've let your eyes adjust to the dark, you'll see that glowing band across the sky that we call the Milky Way, and it's stunningly beautiful. And you might have been able to see tens, even hundreds of other stars. And for thousands of years, that was astronomy, the stuff that our eyes could see. But 400 years ago, we invented the telescope. And ever since then, we've been using telescopes and other instruments to show us things that our eyes can't see on their own, to go beyond what our eyes can pick up. A simple thing to do is just use a camera, but instead of taking a quick picture, open the shutter and leave it open for a long time. And when you do that, you gather more light. And so you can see things that are fainter than your eye can see. And this is the kind of thing you get. This is a photograph taken by a team in the Canary Islands. And it's just an ordinary photograph, actually a film camera in this case, it's quite an old one, of this patch of the sky. And you can still see Orion there, but you can also see an awful lot more. You can see that the stars in Orion have very distinct colors. You can see these big red glowing fuzzy blobs. You can see that the Milky Way is no longer just a glowing band across the sky, but it's made of thousands and thousands of individual stars. And so with the right kind of instrument, we can see more. And so we make progress in astronomy, not by building bigger and better experiments, but by finding better ways of looking at the universe. And that means that astronomy is an observational science, not an experimental one. It's quite a subtle distinction, but it's quite an important one. So we don't work in labs, we don't wear white coats, we don't do any of that stuff. We go out to telescopes. This picture here on the right is some of the students from the university out in Tenerife as part of their degree, learning how to use a telescope, because that's part of being an astronomer. Understanding how things work, understanding the laws of physics, that's all important. But until you've got hold of a telescope and you've pointed it at something and you've worked out what you can and can't see, you can't really know what astronomy is. So we've been doing this using telescopes, using cameras, using instruments for hundreds of years to try and understand the universe. And we know a lot. There's a lot of things out there that we now understand that we didn't even 10 or 15 years ago. But there are still some important things that we just don't get, that we just don't understand yet. And some of them might even take you a bit by surprise. This, for example, is an area where there's a lot of research going on, but where we don't have the answers yet: exoplanets. Exoplanets are stars which orbit around, planets which orbit around stars other than the sun. Now, when I started out in astronomy, we knew of exactly 0 of these. Now we know of about 4,000. So we're finding lots of these things. But you'll notice what I've shown you here is not a photograph. This is not an observation. This is a drawing. This is an artist's impression. And the reason I'm showing an artist's impression is because I don't have a decent photograph. These things are very hard to study. We can detect them, but studying them is much harder because they're small, they're faint, and they're really far away. And they're also next to big bright things like stars. So studying them is challenging. So we don't know very much about them. You'll occasionally see things in the newspapers about, Earth-like exoplanet discovered. That's not a very good way of describing it. When a planet is described as Earth-like, it means it's probably roughly about the same size as the Earth-ish. That's as accurate as we get. We don't know if it's anything like the Earth. We don't know what atmosphere it has. We don't know whether it has oceans. We don't know whether it has land. We don't know anything about it because we can't study these things. So it's big, important questions there. Another important question comes from these things, these supernovae. I've mentioned the neutron star in the center, but that big glowing cloud is also quite interesting and important, the remnants of the outer parts of the star. Because during that explosion, the atoms in that cloud get changed. They're stuck together in more complicated ways. They make heavy elements, things like gold, plutonium and uranium and platinum, and all of these elements are made inside these explosions. In fact, most of the different elements in the universe only exist because of these explosions. So a lot of the things that we're made of are out in space because of these exploding stars, and then they go on to make us. So we're made of bits of exploding star. We are genuinely stardust, but there are aspects of that that we don't understand. We don't really understand all of the reactions, all of the nuclear reactions that are going on to make these elements. So basically, we don't understand where our own atoms came from. Very important question that we haven't answered. And then one of my personal favorites, supermassive black holes. Not just any old black hole, but the really big ones. What's not to like? In this movie here, what you're looking at is stars moving around right in the center of our own galaxy. These are very, very hard observations to make. But over the course of 10 years, some stars were followed night after night, week after week, month after month, until we could plot their movement. And you'll see here, we've got a star which has gone round in a very, very nice, neat oval. It's orbiting. And it's orbiting around something underneath that cross. And there are 3 important things that we can work out about the thing underneath that cross. First of all, it's not very big, because if it was very big, the star would have hit it. So it's small. It's invisible. We can't see it. There's no light coming from it. And it's very, very massive. There's a huge amount of stuff there. Somewhere underneath that cross, there is about 3 million times the mass of the sun. 3 million suns squeezed into something tiny and invisible. It's a black hole. It can't really be anything else. And we're finding these things, these supermassive black holes, in the middle of every single galaxy that we look at. If we should be able to find it, we always find it. So they're everywhere, and we don't really understand how they get there. We don't understand how you can make black holes that big that easily. So again, a fundamental question out there that we just don't understand. So these are 3 bits of astronomy, 3 areas of astronomy where there are things that we just don't understand. And the reason we don't understand them is because they all involve changes. Things orbiting, things exploding. And those changes are hard to study because the telescopes we have at the moment, some of them are very big, they're very powerful, but they're not really designed to look at changes. If you go to a telescope, you might have 3 or 4 nights at the top of a mountain using the telescope, and then you come back. And if you want to observe exploding stars and none explodes in the 3 nights you're there, you've just wasted your time. So we need a different way of using telescopes. And these changes are everywhere. This, for example, is a movie of the sun. Not the sun as we're used to seeing it, with visible light that our eyes can see, although obviously you shouldn't look at the sun, you can damage your eyes. But this is a movie, a speeded up movie of the sun in X-rays. Now, X-rays are really hard to make. In order to make normal light, the stuff that our eyes can see, you just need to be quite hot. few thousand degrees centigrade, and anything glows a kind of yellowish color. But to make X-rays, you've got to be a few million degrees centigrade. So this is much hotter, and it's active, and it's dynamic, and it's changing, and there are explosions. And there are lots of things about this that we don't understand and that we need to. The big explosions on the sun can actually affect us now. They can do things like break GPS satellites. They can destroy electricity grids if they're really extreme. So we need to understand these things, not because we want to stop them. We can't stop these happening. The scale here is very difficult to get your head around. But if you look at one of these little green blobs like that one, that little green blob that you can probably just see there, that's about the same size as the Earth. So these are very big explosions. We're not going to stop them happening. But if we can predict them, we might be able to stop any damage they do. So understanding how the sun changes is important as well as interesting. But we don't really understand it because we haven't been studying the sun in enough detail for long enough with these kinds of instruments. And sometimes you get changes that take you by surprise. So this is another movie of the sun, but this isn't taken by $500 million of space telescope. This is taken by me with a telescope about that big, in the docks in Birkenhead in the rain. Now, there was a good reason for doing this, and the good reason was that little dot there. That little dot you can just see in the middle of the screen. And that, believe it or not, is Mercury. So this was the transit of Mercury a few years ago. Not the most recent one, the one before that. And I thought it would be a really good idea to get a video of the transit of Mercury. So I got up very early in the morning because this started at sunrise in the summer, and I came into work and I got the telescope set up. And just as the sun was beginning to rise and Mercury was just beginning to cross between us and the sun, it began to drizzle. And it drizzled for 6 hours. So I spent 6 hours holding an umbrella over a telescope. I am never doing this again. But it was actually worth it. Not, to be honest, for Mercury. All Mercury did was it was a little dot moving from one side of the sun to the other. And frankly, after half an hour of that, you begin to lose interest. But there was something else, what we call a secondary transit. So the primary transit was Mercury passing between me, where I was observing, and the sun. But just very briefly, for one moment, I got a secondary transit, something else passing between me and the sun. And if you look at this bit of video really closely, you might just be able to spot it. So look really closely when I play this video. Okay, there it goes. I'm going to play that one again because I know it doesn't always pick up on people's bandwidth if you don't catch it. There we go again. So, okay, there's not a huge amount of science in that, but I'm quite proud of it. But the reason I'm showing you this is not because it's a particularly fascinating thing to watch or because I'm particularly clever to have got it. I'm not clever. I'm lucky. I couldn't actually have predicted this. It's a Ryanair flight. Nobody knows what's happening. The reason I got this was not because I'm clever, but because I was lucky and I was in the right place at the right time. And that's often the case in astronomy, and indeed any other science, but I think particularly astronomy. Sometimes the most interesting stuff is the stuff that you discover by accident. And you're more likely to discover something by accident if you look at something that's never been looked at before, or you look at it in a way that's never been looked at before. And that brings us to what I call dynamic astronomy, or time domain astrophysics, as some people call it. And this is deliberately studying how things change. Not just looking once and then going away and looking at something else, but coming back time after time after time to look at the same things and see how they change. And for that, we need a new kind of telescope. Not the sort of telescopes where you travel to the top of the mountain, like the picture behind me, and spend 3 or 4 nights at a telescope taking your observations, but a telescope where you tell it what you want it to do and it gets on with it on its own. So it can do things night after night and it can react to sudden changes. And this is the biggest robotic telescope in the world, called the Liverpool telescope. It's not in Liverpool. I have to stress that. I was giving a talk in a school a little while ago, school in Manchester actually, and I was talking to the pupils about telescopes and where you put them, and why we wouldn't put the telescope in Liverpool. And I was asking the students, why wouldn't you put a telescope in Liverpool? And there were some very nice answers. There's a lot of light pollution, the weather's not very good. But some little kid put his hand up and said if it was in Liverpool, somebody would nick it. That's not why we put it on this mountain. This is La Palma in the Canary Islands, and the reason that the telescope is there is it's because it is one of the best observing sites in the world. That's a telescope itself. You can see there's a person standing at the bottom there to give you a sense of scale. And the place we put it is this. This is the Observatorio de Roques de los Muchachos, the Observatory of the Friendly Rocks. And there are lots of telescopes up there. And the Liverpool telescope you can just see poking up there. And the reason there are lots of telescopes is because the sky at the top of this mountain is incredibly clear. You're above most of the clouds. You're high enough for that. But it's also very stable. La Palma is a very sharp island. It goes straight up from the sea in all directions. And so the air traveling across the ocean, instead of going over the top, tends to go round. And that means the air above stays very stable, which means stars don't twinkle very much. Twinkling stars is caused by movement in the air. And if the air isn't moving, your stars don't twinkle. Your pictures are much, much clearer and sharper. So it's a beautiful, beautiful place. And we've got our telescope at the top there. Now, there are other bigger telescopes. In fact, the largest optical telescope in the world is on La Palma. And it's got a mirror 5 times wider than our own. The thing that makes this one special is not how big it is, but how it works. And I just wanted to talk you through that so that you can see how we're able to do interesting science with this telescope. So instead of giving an astronomer 2 or 3 nights on a telescope and them traveling to the island and so on, what we do is we collect what we call observing programs. These are descriptions of what astronomers want the telescope to do for them. So it might be look at the same star every night for a year. It might be look at that star every night for a year, but if it's gone above a certain level of brightness, then it means it's doing something interesting. So look at it every hour until it drops down again. Or it might be wait for a star to explode and then observe it as quickly as possible. So all of these different ideas, they're gathered together. The Telescope Management Centre is in an office in Liverpool, basically. And we send that all out to La Palma over the internet to the telescope, and we go to bed. There is nobody operating this telescope. It's all done by the computer systems on the island. And then while we're asleep, those computer systems look through all the things that the telescope could be doing, and from minute to minute, second to second, decide what is the best thing to do next. And it's doing things like checking the weather. It's got its own little weather station. It's looking at the data it's just taken to see if there's anything interesting in it. It's getting information from other telescopes and satellites around the world in case something as sudden has happened. And it brings all that together, minute to minute, second to second. It's coming up with the best thing to do next. The next day we wake up, we download those results, and we do the science with them. And that's a completely new way of running a telescope. It turns out it's also quite a good way to run a telescope during a pandemic. This wasn't part of the original plan, but when COVID hit, we were able to keep operating the telescope because it didn't need any people there. There was nobody needed to travel around. So I think it's one of the only large telescopes in the world that has kept operating right the way through the COVID pandemic, which is an unexpected bonus of robotic telescopes, but a nice one. Now, because this is a bit unique, in fact, it's entirely unique, there isn't anything else like it, a lot of people want to use this telescope. But because you don't have to give it to one astronomer per night, but it can be shared among lots of people, then lots of people can use the telescope. So at John Moores at the university, we get quite a lot of time on the telescope because we own it. Astronomers in Spain get quite a lot of time on the telescope because La Palma is a Spanish island, and that's part of the agreement. But also, any other astronomer in the world can apply for time on the telescope. And if they've got a good idea, they will get the observations. And I do mean any astronomer, by the way, not any professional astronomer. Anybody with a good idea can apply for time. And if the idea is good enough, the observations will be taken for them. And we do have several non-professional astronomers, so-called amateur astronomers, who are using the telescope to do some research, which I think is a really nice thing to be able to do. But as well as that, people who are not doing research can use the telescope. So one of the things that got me involved in the project in the first place, sort of 20 years ago now, is the National Schools Observatory. This is the idea that schools around the country can use the telescope for themselves. Any school in the UK or Ireland can sign up completely free and get their own observations with this telescope. And again, that's a pretty unique thing to be able to do, quite an exciting thing to be able to do. Wish I could have done that when I was in school. So I'm lucky enough to run that project. And if anybody wants to do any more about that, just ask me at the end. And also, obviously, our students. We have our degree programs, but we also run short distance learning courses. And the students on those courses also get to use this large telescope so that they can learn what it's like to get real data from a telescope and learn how to deal with it and learn how to make measurements from it. And it can take nice pictures. This is an observation of a star-forming region called Messier 20, which was taken for a student, Bryn Davies, who's in North Wales. And he wanted to look at stars forming, so we were able to take this picture. And he could study this and learn from it, but it also looks nice. And that turns out to be quite important. A few years ago, I did a kind of impromptu survey of astronomers, professional astronomers at a conference. And I just asked them what got them interested in astronomy and science in the first place. And there were lots of reasons. Some it was a television program, some it was a relative, but quite a few people said, I saw a really nice picture and wanted to know what it was. And so we do spend time on this telescope, not a lot of time, but some of the time on the telescope, just getting nice pictures for people, because that's quite inspirational. So that's the background to how the telescope works. What I want to do quickly now is run through some of the interesting science that it's been able to do. Now, it's done a lot. This is a list of just some of the more recent science highlights. And it varied. I'll be coming back to a couple of these later, but it gives you an idea of the range where we talk about things like anything from looking for planets going around other stars through to novae, which are kind of small exploding stars, and supernovae, which of course are bigger versions of the same thing. We're studying black holes, both ones in the middle of galaxies, but also smaller ones, which are currently destroying stars, and we can watch stars spiraling in and being destroyed. And then we've got gamma ray bursts, which are the biggest explosions in the universe since the Big Bang. They're absolutely enormous, and we don't understand them. So we want to know more. And so again, there's been a lot of work following those things up. And as well as all that, we've got about 4,000 schools involved, and they've taken nearly 200,000 observations between them. So all of this is happening on the same telescope. So if you're a 13-year-old pupil in a school and you take an observation from this telescope, the next observation might be looking at a star that's just exploded. All of this is happening together, which I think is really exciting. But I wanted to go through a couple of examples of this science in a little more detail to show you how this telescope is able to contribute. And I'm going to start with near-Earth objects. Now, near-Earth objects are objects that get near to the Earth, hence the name. Astronomers are not very good at naming things. We have a tendency to be a bit literal. Some of you may know that the largest telescope in the world is officially called the Very Large Telescope. That is its name. The next generation of large telescopes are going to be, the next one is going to be called the ELT, the Extremely Large Telescope. Seriously. There's even plans for one called OWL, which I thought was a great name until I discovered that OWL stands for Overwhelmingly Large Telescope. But they may not be imaginative, but at least they're descriptive. So near-Earth objects are ones where there is a chance, albeit very small, that something like this might happen. Now, this is not a photograph. This is an artist's impression. But this is the kind of thing we think happens when a big asteroid hits the Earth. And this is the kind of thing we think wiped out the dinosaurs. To give you a sense of scale here, that splash there is about the same size as Germany. So these are very dramatic. Now, when this happened 50 million years ago and the dinosaurs were wiped out, from our point of view, that was a really good thing, because with the dinosaurs gone, we can take over. Great. But if it happens again, then there's a chance that we're the ones that get wiped out and something else takes over, maybe cockroaches. Cockroaches can survive anything, so that they'd be a good bet for the next sort of master race, if you like, of Earth. Now, I'm not saying we're doing a particularly good job of running the Earth at the moment, but that doesn't mean we necessarily want to be wiped out. So finding these things before they get here and stopping them hitting is probably a good idea. So we need to study these things. Now, asteroids are basically just small rocks or large rocks, but they're basically rocks and they're orbiting around the sun. And if you look in textbooks or on Wikipedia or something like that, you'll see a diagram like this, which has the sun in the middle, and then the orbits of some of the planets I've drawn on Earth, Mars, and Jupiter. And between Mars and Jupiter, you get this thing called the asteroid belt with all the asteroids in it. That's a nice picture. It's simple, it's clear, it's easy to understand. It's also wrong. This is not where all of the asteroids are, it's where most of the asteroids are. If instead of this nice, neat little diagram, we do a plot, a graph of where all the known asteroids actually are, it's messier. There are lots in the asteroid belt, so many that it just becomes this blur, but there are some that are further out, and there are some that are in here, the ones in the middle. And they're the ones which can get close to the Earth. They're the ones we want to track. And we know they occasionally hit, not just because the dinosaurs aren't there, but because there are big holes all over the Earth, things like this. This is a hole in Arizona called the Barringer Crater. And we know this was made by an asteroid about 50,000 years ago. It's about a mile across, basically, a couple 100 meters deep. And the asteroid that made this was about 40 meters wide and made of solid iron, actually. About 1 in 10 asteroids are made of iron rather than rock. So it weighed about 300,000 tons. And when it hit the ground, it was moving at roughly 25 times the speed of sound. And that vaporizes the asteroid, but it makes a big hole. Now, that's a very big lump of metal, and it's moving very fast. But for an asteroid, that's tiny. We're not that worried about things like this, to be honest, because it's just not very big. If something like this hits the ground, all it does is make a very big hole. And generally speaking, they're going to hit places that nobody really cares very much about, deserts, oceans, Manchester, things like that. So we're not that concerned about these. It's the bigger ones, 10 or 100 times bigger than this. Because when they hit the ground, they don't just make a bigger hole, but they throw huge amounts of dust and soot and ash right up into the air. And it goes to the top of the atmosphere and it spreads out until it covers the entire globe and it blocks the sunlight. That's what does the damage, because when that happens, it gets really cold. Not cold like we've had the last week or so, but really cold. Cold enough for the oceans to freeze over completely. And that is what would wipe us out. So we need to find these things before they get too close and do something about them. And robotic telescopes are really good for this. They're not so good for finding them, actually. You need smaller telescopes with bigger cameras for that, basically. But they're very good for following up, because when you found something that might be a near-Earth object, you need to check exactly what it's going to do for the next 50 or 100 years to see whether it is actually likely to hit the Earth. So we're very good at following these things up. The idea is very simple. Something that might be a near-Earth object is detected by one of these smaller specialist telescopes, a survey telescope. We then estimate what the orbit is going to be. And at this stage, it's only a guess, but it's good enough to be able to point the telescope, the Liverpool telescope, in roughly the right direction and see if we can observe it again. We then find the asteroid in those observations and use the new positions to calculate a more accurate orbit. Sometimes you need to repeat those stages a couple of times, but once you've done that, you then can predict exactly where that asteroid is going to be any minute for the next 100 years. And if at any time in the next 100 years it's going to be in the same place as the Earth, then we start to worry about it. 99.99% of the time it's not, and we can move on. But there is a slight problem with this, and the problem is the third step, the asteroid detected in the observations, because everything else we can get computers to do perfectly, but it's very hard to write a computer program that never makes a mistake when looking for the asteroids in the observations. And so to be absolutely sure we haven't missed one, particularly one that's doing something weird, because they're the most interesting ones, we need people to look at these observations. But there are lots of asteroids and not very many astronomers who study this. And so a few years ago, we were sitting down with this problem and thinking, well, we've got to find people to look at these things, but we don't have the time. We're going to miss some if we rely on us. So we decided what we wanted with lots of people with very little, with loads of time on their hands, with very little to do. And then we thought about this. And we thought, we know exactly the right people. We call them children. So what we did was we set up a project on the National Schools Observatory website where we take the observations, we put them straight on the website, and school students, school children all over the world help us to find the asteroids. And I thought we'd have a quick go at doing that now, just so you can get an idea of how difficult it is. This is an observation that contains an asteroid. Now, I'll give you a clue in case you think you've found it. It's not the big bright thing up there. And the reason you can't see much, if anything else, is because this is an image straight off the camera. It hasn't been processed. And so what we need to do is put it into some software and try and bring out more of the details. And that's fairly easy to do. You change it until you start seeing something a bit more like this. And when you've processed it enough that the sky has turned a kind of dark gray rather than a pure black, then you're probably seeing everything there is to see. And now you can definitely see the asteroid. And I'd just like everybody to quickly look at this and see if they can work out which one of these little dots is the asteroid. So there's one asteroid and all the rest are stars, basically. So just give you a few seconds to look at that, see if anybody can work it out. If there's two of you there, have a competition. One of you point at what you think is the asteroid and see if the other person agrees. Now, if there are two of you there, you've probably chosen different things. And that's because it's not easy just looking at one observation. But of course, we don't do this with one observation. We have a big advantage with asteroids in that if you come back a few minutes later and take another observation, the asteroid will have moved and the stars won't. So if we take several observations and show them one after the other, we call it blinking, then anything that moves is an asteroid. And that's what we've got here. And if you look at this, you will see right near the middle here, something moving in a nice straight line. And that's the asteroid. That's how easy these things are to spot. You may see another couple of other weird things. There's a weird flash down here every so often. There's another little speck up here that does the same thing. That's neither an asteroid nor a star. That's a thing called a cosmic ray. That's actually a particle smaller than an atom hitting the camera. And so we need to have at least 3 and preferably 4 observations so we don't get confused by a couple of cosmic rays. But basically, if you've got 3 or 4 observations, asteroids become very obvious. And so, as I say, we've got students all over the world doing this, but we always need more people to help. So if you're interested, that's the website there. We have new observations coming in typically once or twice a week. And the sooner people look at it and report back, the more chance we have of working out exactly what's going on. So if you're interested, do please go along to that website and give us a hand. It would be great. The final thing I want to very quickly talk about are exoplanets. There are lots of techniques for finding exoplanets, but one of the most successful is a thing called the transit method. And this is the idea that if you've got a planet going around a star and it happens to be orbiting along the line of sight that we're looking at, then once every orbit, it will pass between us and the star. Now, we won't see it like this. This is another artist's impression. We won't get a nice picture of it. But while the planet is there, there's a bit of the light from the star that isn't reaching us anymore. And so the star will get a little bit fainter. And then the planet will orbit around a bit further and it will get back up to normal brightness. And then the next orbit, it will dip and come up and dip and come up. And so if you keep looking at how bright stars are night after night after night after night, you will find planets. This has been very successful, and it's found one of the most fascinating systems of planets around a star that we've yet come across. And that's known as TRAPPIST-1, found by the TRAPPIST telescope and the Liverpool telescope and others. And this has got 7 planets which are quite like the Earth, all going around one star. And this shows you a map on the right-hand side of what this planetary system, this kind of extrasolar system, would look like from above. So you have the star in the middle, and going around it, we have all of these different planets. On the left, you can see the change in brightness of the star as each one of these planets goes past. So you can see how they're detected. But the most interesting thing is the gray bit on the diagram on the right, that sort of gray circle. Because any planet inside that gray circle is likely to have a temperature somewhere between 0 degrees centigrade and 100 degrees centigrade. In other words, it's the right temperature for any water on the surface to be liquid. Colder than that, it turns into ice. Hotter than that, it will all evaporate. And we're pretty certain that if we're going to find life that's anything like us, anything we can actually recognize, you're going to have water, liquid water. So they're planets we can look at to try and find life. Can't do it yet, but with the next generation of telescopes, we should be able to study these things and look in their atmospheres for the telltale signs that there might be life there. So I think there's a very good chance that either in the next 20 years, we will find life somewhere else in the universe, or we will discover that we are incredibly rare and life is incredibly rare, and we will know for certain. Either way, that's a really exciting result. And that brings me to the future, because this telescope, the Liverpool telescope, has been operating very well for about 15, 16 years. It's done lots of exciting science, but always in any science, you've got to look to the future. You've got to be planning for what you're going to be doing in 5 or 10 years' time. And one thing that's happening is the rest of the world is starting to catch up with the idea that things in the universe that change are interesting. And in particular, about 10 years ago, the Americans decided this was something that they wanted to take very seriously. And being American, the way they took it seriously was to throw very large amounts of money at it. And they're building something called the Vera Rubin Observatory, which is nearly finished. It will have what's called first light later this year. And this is a very big telescope. To give you an idea of how big, this is the mirror. So it's not finished there. It's not sort of shaped and made shiny, but that's the size of the mirror inside this telescope. But that's not the impressive thing. The impressive thing is actually the camera. Now, those of you who've got digital cameras will know they've got a little chip inside them, which is what detects the light. And typically, the chip inside of a camera is about the same size as my little fingernail. The chip inside the Vera Rubin Observatory is that big. It's one of the largest cameras ever made. And the job of this telescope is to look at the sky, take pictures of as much of it as possible, time after time after time, night after night after night, feed all of those images into a massive computer and find anything that's changed, what we call transients. And the Vera Rubin Observatory is expected to find 1 million completely new transients that we've never seen before every night for 10 years, which is incredibly exciting. But there's a problem, because you might be able to find 1 million of these things every night, but you won't know what they all are. And this telescope can't tell you. Most of them will be able to make a good guess, but of that million, there might be 1 or 2 or 10 or 100, which are really weird, and we have no idea what they are. And to work out what they are, we need a telescope that can take more detailed, precise measurements of those very quickly. In other words, we need something like the Liverpool telescope, but bigger and faster. And so that's what we're building. It has the code name of NRT for New Robotic Telescope. I really hope that that's not the final name, but that might be the name. And the idea is it's going to be next to the current telescope on the Palmer, but it's going to have a mirror 4 times the area, so twice the diameter, so it can gather more light, it can see fainter things. But as well as being bigger, we're going to use modern materials, modern technologies to make it lightweight, so it can move a lot more quickly. The current telescope is quite fast. It can get from anywhere on the sky to anywhere else in the sky and start observing within about 2 minutes. But we want to get that down to preferably less than 30 seconds and ideally 20 seconds. The Liverpool telescope will then have a big camera put on the top, and it could be used to support this. And the two working together will be able to take any of these things that telescopes like the Vera Rubin telescope have discovered and actually work out what they are, work out what the science is. Doing design studies, we've nearly finished the final designs, nearly got a lot of the funding in place. So there's a good chance that this will actually be operating as early as 2025, which is going to be very fast. But that will mean we're just getting there when the Vera Rubin telescope is really getting into its stride. So watch this space. It's going to be a very exciting time in astronomy over the next few years. So just to summarize that, robotic telescopes, things like the Liverpool telescope and its successors, are giving us a completely new way of looking at the universe. We're seeing for the first time systematically how the universe changes. I'm lucky enough to work somewhere where we're leading the way in this, but the really nice thing about astronomy is it's not really competitive, it's collaborative. So because we have this wonderful instrument, because it can do things, it means people all over the world work with us. And we work with other telescopes to help support them and get more of this science done. So this is all going really well, but it is just the beginning. There's so much about the universe that we don't understand, and so much that we will understand as we develop more of these telescopes. We have the survey telescopes like the Vera Rubin. So the next 10, 20, 30 years is going to be incredibly exciting in astronomy. And I'm just really lucky that I'm going to be there watching it all happening and maybe even helping. Now, before I finish, I'm going to do something probably shouldn't do, but I'm going to do two rather shameless plugs for things that are happening. One of them is the Merseyside Astronomy Day. This is an event I organise every year where it's a day where we get people coming in, research astronomers from around the country coming in and talking about their research. But this year it's normally in Liverpool, but this year it's going to be online and it's completely free. So if you're interested, that's the website there, astro.lgmu.ac.uk/mad. And do come along and book a ticket. You will need to book a ticket, but it is completely free. The other thing that's not completely free is an entirely shameless plug. I've written a book, my first book. I'm quite proud of it. It's intended as a kind of introduction to astronomy for people who don't really know very much but would like to know more. I'm told it's quite nice to read. I couldn't judge that myself, but a few people who are normally pretty honest with me have said they liked it, including my brother, which is astonishing. So if you are interested, it's called Everything You Ever Wanted to Know About the Universe. Not exactly a modest title, but it's okay. And it's available in all the usual good bookstores and online and so on. So thank you very much for listening. There's a few websites here with a bit more information, but in the meantime, I'd be very, very pleased to answer any questions that you've got. So thank you very much.
Thank you, Andy. That was very, very interesting. And we've got some questions coming in. So let's see how we go. Right. I'm going to have to peer at my screen because my questions are very small and my eyes are not as good as they used to be. So first question, this is from an anonymous questioner. What challenge does dark matter pose to astronomy, if any? And do we know what it is yet?
I'll start with the second question first. No, we haven't got a clue what it is. We know there must be quite a lot of it out there because things move around as if there was a lot more stuff than we can see. And we know it's not made of normal atoms because if it was, we'd have seen it by now. So it's made of something we've never seen before. And there's more of it, a lot more of it than there is normal stuff that we're made of. So it pretty much has to be there, but we don't know what it is. So the challenge it poses is we've got this really embarrassing thing that we haven't answered yet. But the nice thing about doing science is everything you haven't answered is something to work on. So the exciting thing about this is we will eventually work out what this is. It might be, the answer might come from astronomy, it might come from particle physics, but we will work out what this stuff is. And then we'll have discovered something fundamentally new about the universe. And initially that will just be interesting and exciting. But who knows what that will lead to? It will help us to understand gravity better. It will help us to understand the nature of matter better. And in 20, 50, 100, 200 years' time, who knows what we can do with that knowledge? Maybe we can use that to solve problems, or maybe it can just be something we really want to know the answer to. So yeah, it poses an interesting and exciting challenge, and we haven't got a clue what it is yet, which is why it's fun.
Okay, next question. This is relating to Betelgeuse, which is a star not too far from us. When is Betelgeuse going to explode, and what effect will it have on Earth?
So those of you who haven't come across this, Betelgeuse is a star which has a very good chance, not a certainty, but a very good chance of turning into one of these supernovae, one of these giant exploding stars. The answer to when it's going to explode is soon, but this is soon in astronomical speak, which means sometime in the next 100,000 years, which to us is soon. It might have just happened and we'll walk outside tonight and see it, or it might not happen for 50,000 years or more. The effect it will have on the Earth is not dramatic, actually. It's not that close to us. So it will be very bright. It'll probably be bright enough to see it during the day. But it's far enough away that we're not going to get any radiation, and don't have to worry about things like neutrinos and that kind of stuff. So it will be interesting rather than dramatic. But we will learn a huge amount about exploding stars. One thing to bear in mind is that although we talk about supernovae and all these exciting things and how important they are, we haven't had a supernova that we've seen in our own galaxy since the telescope was invented. If we get one as close as Betelgeuse, it will be party time for all astronomers, because that's what we've been waiting for 400 years. So it will be awesome.
Okay, I hope you're right about that. You've already frightened me to death about asteroids. So I'm glad to hear that Betelgeuse poses no immediate threat to us. So next question is from Philippa Scott. Are you confident that we can still have funding to share information with Europe?
That's a tricky one. In terms of sharing information, yes, because we don't care about the money. That's not the point. All astronomy is shared with all astronomers. In fact, it's shared with everybody. For example, if you want to, you can come along to the Liverpool Telescope website there, and you can get any observation that anybody has ever taken with that telescope for yourself. It's all free. And that's true with any telescope in the world. That's how they work. And, if you find out something new, you write a paper and tell everybody, because otherwise, what's the point of finding it out? So sharing information isn't a problem. Funding can be a problem. At the moment, well, basically until the 1st of January, it's hard to put exact numbers on this, but roughly a third of all the funding in the UK for astronomy came from European funding. And we don't know what's happening to that money anymore. So that could be a major disaster, or it could be that something will happen to replace it. And nobody's given us an answer to that yet. So all I can tell you is we haven't got a clue. But we would love to know, because it really will make life a lot less stressful when we know what's happening there. The thing about the European funding for astronomy is basically every country that was part of the EU and still is puts money into a big pot, and then everybody applies for it. We're really good at writing applications, so we've always got a lot more back than we put in, and it's difficult to see how that can continue when we're not paying into the pot. It's one of those things.
Okay, next question is from Mark and Janet Troe. And this is an interesting one. I've often wondered about this myself. If these, you used one here, these artist impressions of features in space, they're saying, how far are they scientifically accurate, and to what extent are they mere artistic impressions?
It does depend on who's doing the art, who's paying them to do the art, and what information you already have. So, for example, some will be very accurate. You get artist impressions of things like, there's quite a common one, is two stars orbiting around each other, and you get material falling from one star onto the other one. And we know a lot about those systems. We know the colors, we know the temperatures, we know the sizes, we know the shapes, just from studying the physics. So you can do a very accurate image of what that would look like. And usually, if you want an artist's impression of one of those things, you'll find somebody who will give you something that's very accurate. The planets are a little bit more random, because all we know about them is they're there, and we know their rough size. So what people tend to do for artist impressions of exoplanets is they take a planet in the solar system which is pretty similar in size and temperature, and then they tweak it until it looks a bit different. So they're probably moderately accurate, but we don't know for certain. So it does vary. I quite like using artist impressions as long as it's very clear that's what they are. But occasionally you see things. I do love it when I pick up a newspaper or something and look at it, and there's, a very obvious artist impression which clearly has no resemblance to reality at all, and was knocked together by a graphic designer without talking to an astronomer at all. And underneath it says picture of exoplanet 174.7b, and it clearly isn't. So that I find both funny and annoying. But generally speaking, most of the artist impressions that you get, which are put out by scientific organizations, have all of the information that we can possibly put into them done accurately.
Yeah, it's also probably worth saying in this context that Star Trek and Star Wars are not real events or histories. So there are two other questions that Mark and Janet have asked.
Oh dear.
But in the interest of brevity, can you just say yes, no, or in deference to your professional standing, pass?
Right.
Just one of those three. The first question is, does alien life exist? And the second question is, do you know Brian Cox?
So the answer to the first question is probably. And the answer to the second question is met him a couple of times, but don't know him well.
Right, thank you.
Nice guy.
Yeah, okay. From Louise Hammond, Is our universe still expanding? So will the moon move away from Earth?
Now, it turns out that they're both actually, that's actually two questions there, so I can't answer this that quickly. Yes, the universe is still expanding, and we have no reason to suppose it's ever going to stop. But that expansion is only on very large scales. When you start getting down to something the size of a solar system or even a galaxy, the gravity within that, so the gravity between us and the moon or the gravity between us and the sun, stops them moving apart. The gravity is strong enough that they don't move apart. It's a little bit like if you had a balloon and you inflate the balloon, everything moves apart on the surface of the balloon. But if you were to stick a stamp on the surface of the balloon and then blow up the balloon, the stamp doesn't get any bigger because the paper is stronger than the stretchiness of the balloon. And that's sort of what's happening in the universe. So the expansion of the universe is not making the moon move away from us, but the moon is moving away from us. And it's moving away from us because of tides. The tides that we get on the Earth make the water slosh around, basically. That's what tides are. And when you slosh something around, what you're creating is friction. And friction slows things down. So as the tides make the water slosh around, it's very slightly slowing the Earth down. But there's this fundamental law in physics that we call the conservation of angular momentum, but it basically means the total amount of things going round in circles is fixed. So if you slow the Earth down, so it's not spinning as much, then the Earth has to move, then the moon has to move in a bigger circle, so it has to get slightly further away. So the moon is actually drifting away from us all the time. I think it moves by about half a centimetre a year or something like that. Yeah.
Okay. So the moon's
sorry, slightly complicated answer, but
yeah. Okay. The moon's getting further away, and it's still made of cheese, of course. We have
absolutely, and it's supposed to be delicious.
Yeah, absolutely. The next one is from an anonymous questioner. What improvements would have to be made to the telescopes to be able to view black holes in more detail? And how long do you think it will be until we understand the true crazy nature of them?
That's a really difficult question. Viewing black holes in more detail is a specialist thing. It's not something that any telescope that you build will be able to do. You have to build a telescope where the only job is to image black holes in detail. And there's one at the moment, it's called the Event Horizon Telescope. And you probably saw, what was it, about 2 years ago, there was the first ever observation of a black hole, this kind of glowing orange donut. That one observation, that one picture of a black hole took about 5 years' work. And that was the easiest one. That's why they started with that black hole. It was by far the easiest one to do. To go beyond that, we need much more sophisticated telescopes, which we're not even starting to build yet because they'd be incredibly expensive. So we're not even close to really understanding these things. But we now know it's possible. So we now know that if we decide to put the effort into it and build these giant telescopes that we'd need and put all the effort into the computer software and so on, then it can be done. Whether that will solve it will really answer the questions about them, I don't know. The problem really with black holes is not that we can't see them, but that we can't test the physics of them properly on the Earth. And that's something that the next generation of particle accelerators might let us do, because the next generation of particle accelerators just might let us make tiny little black holes for a tiny fraction of a second. And if we can do that, then we can actually study black holes in detail in a lab rather than trying to build telescopes that look at them billions of miles away. And that gives us a better chance of understanding them. It's not perfect, but it gives us a better chance.
Okay. This one is, well, there's a sort of a number of versions of this question. Meredith and at least one anonymous person has asked, is there anything we can do to prevent nasty things hitting the Earth?
Oh, yeah, I love this. This is great. There are lots of things we can do. The obvious thing is to go and blow them up. But actually, that's a really bad idea. I mean, it gets rid of Bruce Willis, but other than that, it's a bad idea. Because basically all that happens is you blow it up and all the bits still hit you. It's like the difference between being shot with a rifle and shot with a shotgun. Just don't be shot. But what you can do is nudge them out of the way. And there's lots of ways of doing that. You can try crashing a rocket into them. You can try using a giant net and pulling it out of the way. But actually, the the safest way, the way that's not going to cause it to break apart and cause other problems, is to go up and paint one side of the asteroid white, which may sound really weird, but there's a lot of sunlight out in space, and sunlight, any kind of light, gently pushes. Now, you can't feel it, it's a tiny little push, but the light coming, out of my screen at the moment is very gently pushing me backwards. And the shinier I am, the more light bounces off me, and therefore the more I'm pushed. And so if you paint one side of an asteroid white, that side gets pushed slightly more than the other. And that could be enough to just change its orbit so that it ends up missing the Earth. Now, you can't do that a week before it arrives. You've got to do this 20 years before it arrives. But if you do, it will miss. Everything's fine.
So basically what you're saying is we need swing bowlers to become astrophysicists, yes?
Pretty much, yeah.
Okay. The next question, do you think there could be a solar flare that could reach Earth soon? And if are you able to predict them? And how would it affect modern day society?
That's three very good questions there. Yes, there could easily be a solar flare. There's solar flares every year. Some of them point towards the Earth. The really big ones are rarer, but they're still, every 40 or 50 years. They're not that rare. So there's a good chance that sometime in the next year or 10 years, there will be a big solar flare that points towards the Earth. At the moment, we can't predict them, but we get a bit of warning because we've got a network of satellites which can see the flare leaving the sun, and the flare is moving slower than the speed of light. So we get information from the satellites telling us it's coming, and you can get an hour, 2 hours notice, something like that, maybe even more. So we get a little bit of warning. Without that warning, the damage could be considerable. It can knock satellites out of orbit. Might destroy the national grid. It will break the internet. Mobile phones won't work. Things that we didn't care about 100 years ago, but which now are quite serious. But with enough warning, you can protect all those systems. You can throw a circuit breaker on the national grid, and you might have a power cut for half an hour, but nothing will be damaged, and you turn it on again afterwards. You can do the same equivalent thing with sort of internet servers and mobile phone masts and so on, just temporary, say 5 or 10 minutes of loss of service rather than any actual damage. So as long as we have that advanced warning, we will be fine. Yeah.
Okay, thank you. I think we were over time, but there's one last question. It's another disaster question, I'm afraid, but yeah. And then we'll wrap the session up. I think there are a couple of other people coming questions, but we could go on all evening. It's been a fascinating talk. This is the final question then, again from an anonymous person. Is it possible that Earth would be hit by a comet? And if so, how devastating would that be?
Yes, it is quite likely. It's less likely than asteroids just because comets
likely?
Are rarer.
What do you mean likely?
At some point in the next million years, there's a good chance that the Earth will be hit by a comet. So if you're planning on living more than 1 million years, worry about this. The chances of it hitting in the next 50 years are low. The thing about comets is they do a similar sort of damage to asteroids, but they're made of ice rather than rock. So they tend to spread out as they go through the atmosphere. And so they spread out their damage a bit more. It's actually quite likely that some of the mass extinctions from way before the dinosaurs were caused by comets, in fact, rather than asteroids. But we're more likely to be hit by an asteroid than a comet. So they're the ones we're concentrating on at the moment. Once we've worked out what's happening to all the asteroids, then we can start looking at the comets just in case.
Okay, I just hope there's no one from the insurance industry watching this. Okay, thank you very, very much. That's been a wonderful, very interesting lecture. I found it absolutely fascinating, and I'm sure if I can speak on behalf of our attendees, that they have too. So thank you so much for doing that. It's wonderful, and I hope that people will pick up on these connections here. We will be putting the talk on YouTube, and it has been recorded, and it will be available again off our website. So if there's anything you missed, you can come back and do that. And there are lots of connections and things you can take up in future. And maybe we'll get a couple of young astronomers out of this talk. People who are really sort of, you know, thinking about now that maybe they should be doing astrophysics at university or whatever. So thank you very much for that. Can I just mention that there are 2 more talks in the festival. So there is time to register for those talks coming up. Tomorrow night we have a talk on the by the Friends of the Flax Mill, the historic and very important historic monument in Shrewsbury, about how the various innovators in the town are represented by the many number of innovations that embodied in that building and the engineering expertise in the town of Shrewsbury. And on Wednesday we have a talk about Darwin's Garden, the part of the mount where Darwin was born, his old family home, where he lived when he wasn't on the Beagle or whatever for the first 27 years of his life, and fell in love with ecology and nature studies because of the large garden that he had there, and all his early work and all his early interest was centered on that garden, and it's still preserved and developed in the same way. So that's a really fascinating talk on Wednesday night. That's the only talk, incidentally, where there's a small fee to join. I think it's £3 or something, and that's because it's in aid of the Shropshire Wildlife Trust. So it's a good cause. Again, finally, then it only remains for me to say thank you very much for such a great talk, and
Thank you.
Thank you very much, and thank you all for attending, and good night. Thank you.